Right now, as you read these words, the entire Milky Way galaxy, all 200 billion stars including our Sun and every planet orbiting those stars, is racing through space at 2.2 million kilometers per hour towards something we cannot see, cannot identify, and cannot fully understand. We are passengers on a cosmic journey toward a destination that remains hidden behind veils of dark matter and cosmic distance, pulled by gravitational forces so vast they dwarf anything in our experience. We've always imagined that galaxies drift randomly through space, perhaps slowly separating due to cosmic expansion, following predictable paths determined by the gravity of visible matter. We believed that if we could map all the stars and galaxies around us, we could understand the forces shaping cosmic motion. We were profoundly wrong about the nature of galactic movement and the invisible architecture that governs the universe's largest structures. Here is what makes this revelation so unsettling. The force pulling our galaxy isn't coming from any concentration of visible matter we can identify. When astronomers map the distribution of galaxies, stars, and known matter in the direction of our motion, they find insufficient mass to account for the tremendous gravitational pull dragging the Milky Way across hundreds of millions of light years of space. We're being pulled towards something that appears to be largely invisible. The mathematics behind our galactic motion are staggering in their implications. The local group, our galaxy cluster, containing the Milky Way, Andromeda, and dozens of smaller galaxies, is moving at 627 kilometers per second relative to the cosmic microwave background radiation. This motion isn't random drift or expansion-driven separation. It's directed, purposeful movement toward a specific region of space or something massive enough to influence galactic motion across vast distances remains hidden from our direct observation. Leading cosmologists like Alan Dressler, Sandra Faber, and their Seven Samurai collaboration first mapped this cosmic flow in the 1980s, revealing that our galaxy is part of a vast river of galaxies, all streaming toward the same mysterious destination. Their observations showed that thousands of galaxies across hundreds of millions of light years are participating in this coordinated motion, suggesting gravitational influences that operate on scales larger than anything in our previous cosmic understanding. But perhaps the most disturbing aspect of our galactic journey is its inevitability. We cannot alter course, cannot slow down, cannot escape the gravitational grip that pulls us toward the unknown. Every second that passes, our entire galactic neighborhood moves 627 kilometers closer to whatever lies hidden in the direction of the constellations, Hydra and Centaurus, carrying Earth and everything we've ever known toward a cosmic destination we may never fully comprehend. Tonight, we'll explore the discovery of our galaxy's mysterious motion, investigate the invisible forces that could be driving this cosmic migration, and confront the unsettling possibility that the universe contains gravitational structures so massive and so hidden that they shape galactic motion across distances that exceed our current understanding of cosmic architecture. We'll journey through the observations that revealed our cosmic drift, examine the candidates for what could be pulling us from the Great Attractor to dark matter structures to exotic physics beyond our current theories. We'll discover how entire clusters of galaxies participate in flows that suggest cosmic structures larger than the largest visible formations, and we'll investigate why these gravitational influences remain largely invisible despite their enormous effects on galactic motion. By the end of this exploration, you'll understand why our galaxy's motion represents one of the most profound mysteries in modern cosmology, why the forces driving cosmic flows challenge our understanding of matter and gravity, and what it means to exist within a universe where invisible structures exert influence across distances that dwarf individual galaxies while remaining hidden from direct observation. This isn't about distant theoretical physics or abstract cosmological models. This is about the actual motion of your home galaxy through space. driven by forces we cannot see toward a destination we cannot identify. Every moment of your existence occurs within this cosmic journey toward the unknown, making you a passenger on one of the universe's most mysterious migrations. The invisible cosmic structures that pull our galaxy operate on scales that challenge human comprehension. They could be concentrations of dark matter more massive than anything we've previously discovered, exotic gravitational effects from regions of space we haven't properly mapped, or evidence for physics beyond our current theories that operates on cosmic scales. If you're ready to discover what invisible forces are pulling your home galaxy through space toward an unknown destination, subscribe and hit the thumbs up button. And here is a question that will change your perspective forever. If something powerful enough to move entire galaxies remains hidden from our observation, what other cosmic structures might be influencing our cosmic environment without our knowledge? Share your thoughts in the comments. I'll pin the most thought-provoking response. The evidence for our galaxy's mysterious motion toward invisible cosmic structures is about to reveal why we are all passengers on a journey towards something that challenges our understanding of matter, gravity, and the fundamental architecture of the universe. What you're about to learn will transform your understanding of cosmic motion and our place within gravitational flows that operate on scales larger than anything in our direct experience. Now let's begin our investigation into the invisible destination that's pulling our entire galaxy through space. Chapter 1. Discovering Galactic Motion. The revelation that our galaxy is racing towards something invisible began with one of the most sophisticated astronomical surveys ever attempted, mapping the motion of thousands of galaxies to understand how cosmic structures move through space. What astronomers discovered challenged everything they thought they knew about galactic motion and revealed that our cosmic neighborhood participates in flows so vast they require invisible gravitational sources to explain. The cosmic microwave background radiation, the afterglow of the Big Bang, provides the ultimate reference frame for measuring cosmic motion. This ancient light, emitted when the universe became transparent 380,000 years after the Big Bang, comes to us from all directions with nearly uniform temperature. But precise measurements by satellites like COBE, WMAP, and Planck revealed a subtle asymmetry. The radiation appears slightly warmer in one direction and slightly cooler in the opposite direction. This temperature dipole in the cosmic microwave background immediately told astronomers something extraordinary. Our entire local cosmic environment is moving rapidly relative to the universe as fundamental rest frame. The Doppler effect from our motion creates the temperature asymmetry, with radiation appearing blue-shifted and warmer in our direction of motion and red-shifted and cooler in the direction we're moving away from. The Seven Samurai collaboration, Alan Dressler, Sandra Faber, David Burstein, Roger Davies, Donald Lindenbell, Roberto Tarlovich, and Gary Wegner conducted the definitive study that mapped the scope of cosmic motion in the 1980s. Their survey measured the distances and velocities of galaxies across a vast region of space, revealing that our galaxy's motion is just part of a much larger flow involving thousands of galaxies across hundreds of millions of light years. Their observations showed that the local group, containing the Milky Way and Andromeda galaxies, is moving at 627 kilometers per second in the direction of the constellation Hydra. But even more remarkably, they discovered that this motion isn't unique to our local environment. Galaxies across enormous distances are all participating in coordinated flows toward the same general region of space, suggesting gravitational influences that operate on scales larger than individual galaxy clusters. The technique of measuring galactic motion involves comparing two different methods for determining distances to galaxies. The redshift distance relationship from Hubble's law tells astronomers how fast galaxies should be moving due to cosmic expansion alone. But when they measure actual galaxy velocities using standard candles like Type Ia supernova or surface brightness fluctuations, They find systematic deviations from pure Hubble flow that reveal additional motion beyond cosmic expansion. These peculiar velocities, motions beyond what cosmic expansion would predict, create a map of cosmic flows that reveals the gravitational influence of both visible and invisible matter. Galaxies closer to massive structures move faster toward those structures, while galaxies in cosmic voids move more slowly or even in directions opposite to the local expansion. The pattern of peculiar velocities traces the gravitational landscape of the universe. The WMAP redshift survey and the 6-degree field galaxy survey extended measurements of galactic motion to even larger scales, confirming that cosmic flows operate across distances of several hundred million light-years. These surveys revealed that our galaxy's motion toward Hydra is part of an even larger flow pattern, where thousands of galaxies stream toward a common convergence zone in space. The Tully-Fisher relation, which connects galaxy rotation speeds to their intrinsic brightness, provided an independent method for measuring galaxy distances and thereby detecting peculiar velocities. Sandra Faber and Robert Jackson, as fundamental plane relation for elliptical galaxies, offered another distance indicator that helped map the three-dimensional structure of cosmic flows with increasing precision. Redshift-independent distance measurements using Cepheid variable stars, measured by the Hubble Space Telescope's key project, provided crucial calibrations for understanding the scale of cosmic flows. These measurements confirmed that our galaxy's motion involves genuine gravitational acceleration toward massive structures rather than systematic errors in distance measurements or cosmic expansion models. The discovery that cosmic flows extend across such vast distances immediately raised profound questions about the source of gravitational attraction. When astronomers tallied up all the visible matter stars, gas, dust, and known galaxy clusters in the direction of our motion, they found insufficient mass to account for the observed acceleration. Something invisible must be providing the additional gravitational pull required to drive such large-scale coordinated motion. Computer simulations of cosmic structure formation based on the lambda-CDM model of cosmology predict that dark matter should form filamentary structures and massive concentrations that could drive galactic flows. However, the simulations initially struggled to reproduce the specific amplitude and direction of observed cosmic flows, suggesting that our understanding of dark matter distribution or gravitational physics might be incomplete. The Sloan Digital Sky Survey created the most detailed three-dimensional map of galaxy positions and motions ever assembled, revealing the cosmic web structure of filaments and voids that shapes galactic motion. This survey confirmed that galaxies flow along dark matter filaments toward the intersections where massive galaxy clusters form, but it also revealed flows toward regions where no corresponding visible structures could be identified. Gravitational lensing observations, which detect dark matter through its gravitational effects on background light, began to map the invisible mass distribution that could be driving cosmic flows. These studies revealed that dark matter concentrations often exceed visible matter by factors of 5 or 10, providing potential sources for the gravitational forces pulling galaxies across vast distances. The Cosmic Flows Project, led by teams including Helene Courtois and Brent Tully, used increasingly sophisticated distance measurement techniques to map peculiar velocities across ever larger volumes of space. Their work revealed that cosmic flows operate on scales approaching 1 billion light-years distances, so vast that they challenge theoretical models of how gravitational influences can coordinate motion across such enormous regions. Type Ia supernova observations, originally conducted to measure cosmic acceleration due to dark energy, also provided precise measurements of galaxy peculiar velocities by comparing observed brightness to predictions based on redshift. These measurements confirmed the reality of large-scale flows while adding precision to estimates of their amplitude and direction. The realization that our galaxy participates in cosmic flows fundamentally changed how astronomers think about galactic motion. Instead of galaxies moving independently through space, according to local gravitational influences, the universe revealed itself to contain coherent motion patterns that extend across distances larger than the largest visible structures. This suggested gravitational influences from sources that remain largely invisible. Surface brightness fluctuation measurements, developed by John Taury and others, provided another independent method for measuring galaxy distances and detecting peculiar velocities. These techniques use the statistical properties of stellar populations in galaxy images to determine distances with high precision, confirming the reality of cosmic flows through multiple independent observational approaches. The discovery of our galactic motion toward invisible destinations marked a turning point in cosmology, revealing that the universe contains gravitational influences that operate on scales previously unimagined. The coordinated motion of thousands of galaxies across hundreds of millions of light-years requires gravitational sources that exceed anything in our direct observation, pointing toward cosmic structures that remain largely hidden from view. As you contemplate the fact that your home galaxy is racing through space at 2.2 million kilometers per hour towards something we cannot see, recognize that this represents one of the most profound mysteries in modern astronomy. Every second that passes, our entire galactic environment moves closer to whatever invisible structure is powerful enough to influence galactic motion across distances that challenge our understanding of cosmic gravitational architecture. The discovery of cosmic flows toward invisible destinations opened the door to investigating what could be powerful enough to pull entire galaxies across such vast distances while remaining hidden from our direct observation. We must now explore the leading candidates for the source of this mysterious gravitational attraction. Chapter 2. The Great Attractor Mystery. Deep in the direction of our galactic motion lies one of the most mysterious objects in the observable universe, a coaster gravitational anomaly so massive it influences galactic motion across distances of hundreds of millions of light-years, yet so obscured by dust and foreground stars that it remains largely invisible to optical telescopes. This is the Great Attractor, a cosmic structure whose very existence challenges our understanding of how matter can organize itself on the largest scales while remaining hidden from direct observation. The Great Attractor was first identified through its gravitational effects rather than direct observation. When astronomers mapped the peculiar velocities of galaxies in our cosmic neighborhood, they found that thousands of galaxies across vast regions of space are all streaming toward a common point located roughly 250 million light-years away in the 50 million light-years away in the direction of the constellations Hydra and Centaurus. The convergence of these cosmic flows revealed the presence of something massive enough to influence galactic motion across distances that dwarf individual galaxy clusters. The gravitational influence of the Great Attractor is staggering in its scope and power. Estimates suggest it contains the gravitational equivalent of tens of thousands of galaxies, perhaps 100,000. times the mass of the Milky Way concentrated in a region that appears to contain far fewer visible galaxies than this enormous gravitational influence would require. This massive gravitational deficit creates one of the most profound mysteries in observational cosmology. The discovery of the Great Attractor's location presented immediate observational challenges because it lies directly behind the zone of avoidance, the region of sky where dust and stars in the Milky Way's disk block our view of distant cosmic structures. This cosmic coincidence means that the most gravitationally influential structure in our local cosmic environment remains largely hidden behind our own galaxy's material, making direct observation extraordinarily difficult. Radio astronomy provided the first glimpses through the cosmic dust that conceals the Great Attractor. The 21-centimeter radio emission from neutral hydrogen in distant galaxies can penetrate the dust that blocks optical light, revealing galaxy populations that remain invisible to optical telescopes. These radio observations detected concentrations of galaxies in the Great Attractor region, but not nearly enough to account for the enormous gravitational influence. X-ray observations by satellites like Rosat and Chandra detected hot gas between galaxies in the Great Attractor region, providing evidence for massive galaxy clusters that heat intergalactic gas to millions of degrees. These X-ray sources revealed the presence of matter, concentrations that contribute to the Great Attractor's gravitational field, but again fell short of explaining the total gravitational influence inferred from galactic motions. Near-infrared observations, which can penetrate cosmic dust more effectively than optical light, revealed additional galaxy populations in the Great Attractor region. The 2-micron all-sky survey, 2MASS, and subsequent infrared surveys detected galaxy clusters and superclusters that were previously hidden by dust, contributing to our understanding of the visible matter content in this mysterious region. The Norma cluster, also known as Abell 3627, represents one of the most massive galaxy clusters discovered in the Great Attractor region. This cluster contains hundreds of galaxies and enormous amounts of hot gas detected through X-ray observations, making it one of the largest known galaxy clusters. However, even including massive clusters like Norma, the total visible matter falls short of explaining the Great Attractor's gravitational influence. Gravitational lensing studies attempted to map the dark matter distribution in the Great Attractor region by observing how the gravity of foreground matter distorts the images of background galaxies. These observations revealed that dark matter concentrations in the region exceed visible matter by the typical cosmic ratio of about 5:1. But the total matter visible plus dark still appears insufficient to account for the observed gravitational effects. The Shapley Supercluster, located beyond the Great Attractor, represents another massive concentration of galaxies that contributes to the gravitational field pulling our galaxy. This supercluster contains dozens of galaxy clusters and represents one of the most massive known structures in the local universe. However, its greater distance means it contributes less gravitational pull than its enormous mass might suggest. Computer simulations of cosmic structure formation predict that regions like the Great Attractor should form at the intersections of dark matter filaments, where material flowing along cosmic web structures converges to create massive concentrations. These simulations suggest that the Great Attractor region should contain not just galaxy clusters, but also vast amounts of dark matter distributed in complex filamentary and sheet-like structures. The missing matter problem in the Great Attractor region led some astronomers to propose exotic explanations, including modifications to gravitational physics or the presence of dark matter concentrations that exceed typical cosmic ratios. However, most astronomers believe that improved observations and better understanding of dark matter distribution will eventually account for the gravitational deficit without requiring new physics. Recent observations by facilities like the Square Kilometre Array precursors have begun to map neutral hydrogen distribution across the Great Attractor region with unprecedented detail. These radio surveys reveal galaxy populations and large-scale structure that were previously undetectable, gradually filling in the picture of matter distribution in this gravitationally important region. The Planck satellite measurements of cosmic microwave background fluctuations provide constraints on the total matter distribution in the Great Attractor region through gravitational effects on the ancient light. These observations suggest that the region does contain significant matter concentrations, but also indicate that some of the gravitational influence might come from structures at even greater distances. Peculiar velocity measurements continue to refine our understanding of the Great Attractor's gravitational field through increasingly precise observations of galaxy motions. Modern surveys, like the 6DF Galaxy Survey, and future projects like the Dark Energy Survey provide improved measurements of how galaxies move in response to gravitational influences from the Great Attractor and other massive structures. The discovery that the Great Attractor region contains the Vela Supercluster added another piece to the gravitational puzzle. This massive supercluster lies partially hidden behind Milky Way dust and gas, contributing to the total gravitational field while remaining largely invisible to optical observations. The Vela Supercluster represents one of the nearest major galaxy concentrations and plays a significant role in shaping local galactic motions. Multi-wavelength astronomy has gradually revealed the complexity of the Great Attractor region by combining optical, infrared, radio, and X-ray observations to create comprehensive pictures of matter distribution. These combined observations show that the region contains multiple massive galaxy clusters, extensive dark matter concentrations, and complex large-scale structure that together create the gravitational field influencing local cosmic flows. The relationship between the Great Attractor and even larger cosmic structures has become apparent through wide-field surveys that map galaxy distributions across billion light-year scales. These observations reveal that the Great Attractor represents just one component of a much larger gravitational landscape that includes the Shapley Supercluster, the Perseus-Pisces Supercluster, and other massive structures that collectively shape cosmic flows. Theoretical models of cosmic flows suggest that no single structure like the Great Attractor can fully explain the observed galactic motions. Instead, the flows result from the combined gravitational influences of multiple massive structures distributed across hundreds of millions of light years. This distributed gravitational field creates coherent flows that extend far beyond what any individual structure could produce. The continuing mystery of the Great Attractor demonstrates how much we still do not understand about matter distribution on cosmic scales. Despite decades of increasingly sophisticated observations, the gravitational sources driving galactic motion toward this region remain only partially identified. This suggests that cosmic structure formation and dark matter distribution might be more complex than our current models predict. As you consider that our galaxy is being pulled toward a gravitational anomaly whose sources remain largely mysterious, recognize that the Great Attractor represents one of the most profound unknowns in our cosmic neighborhood. Every moment that passes, our entire galactic environment moves closer to whatever massive structures lie hidden in this region, carrying us toward a gravitational convergence zone that challenges our understanding of how matter organizes itself on the largest cosmic scales. The Great Attractor's influence on our galactic motion demonstrates the power of invisible gravitational structures to shape cosmic evolution across vast distances. But this mysterious region represents just one piece of a larger puzzle involving cosmic flows that extend even further into space, toward destinations that remain even more enigmatic. Chapter 3: Dark Matter Currents. The motion of our galaxy toward invisible destinations involves more than individual massive structures like the Great Attractor. It reveals the existence of vast dark matter currents that flow through space like cosmic rivers, carrying galaxies along filamentary structures that remain largely invisible yet fundamentally shape the universe's largest-scale architecture. These dark matter streams represent the hidden circulatory system of the cosmos, creating gravitational highways that determine how matter moves across distances that exceed our current observational capabilities. Dark matter comprises approximately 85% of all matter in the universe, outweighing ordinary matter by more than 5 to 1. Unlike ordinary matter, dark matter interacts only through gravitational forces, making it invisible to electromagnetic radiation while still exerting powerful gravitational influences that shape cosmic structure formation. The cosmic web of dark matter filaments provides the scaffolding upon which galaxies form and along which they move in vast coordinated flows. Computer simulations of cosmic structure formation such as the Millennium Simulation and the Illustris Project, reveal how dark matter organizes itself into an intricate network of filaments, sheets, and nodes that span the entire observable universe. These simulations show that dark matter doesn't distribute itself randomly, but instead forms coherent structures that channel galactic motion along preferred pathways, creating the cosmic flows that carry our galaxy toward distant destinations. The Via Lactea simulation specifically modeled the formation of Milky Way-sized galaxies within the cosmic web, revealing how dark matter halos grow through accretion along filamentary structures. These simulations demonstrate that galaxies like ours form at the intersections of multiple dark matter filaments, where converging flows create the dense environments necessary for star formation and galactic evolution. Observational evidence for dark matter currents comes from weak gravitational lensing surveys that map how dark matter distorts the shapes of background galaxies. The Cosmic Evolution Survey, COSMOS, and the Dark Energy Survey have created detailed maps of dark matter distribution across vast regions of space, revealing filamentary structures that connect massive galaxy clusters and guide galactic motion along preferred directions. The cosmic web structure inferred from galaxy surveys shows remarkable agreement with dark matter simulations, confirming that visible galaxies trace the underlying dark matter architecture. The 2DF Galaxy Redshift Survey and the Sloan Digital Sky Survey revealed that galaxies align along filamentary structures separated by vast cosmic voids, creating a cosmic web pattern that reflects the hidden dark matter framework. Cold dark matter models predict that cosmic flow should follow the gravitational potential wells created by dark matter filaments. Galaxies falling into these gravitational channels would naturally develop coordinated motions toward the densest regions where multiple filaments converge. This theoretical framework explains why our galaxy's motion appears directed towards specific regions rather than being randomly distributed. The velocity field of galaxies in our cosmic neighborhood shows clear evidence for flow along dark matter filaments toward massive nodes in the cosmic web. Peculiar velocity surveys reveal that thousands of galaxies participate in coherent motions that align with theoretical predictions for how matter should move along dark matter structures, providing observational confirmation of the cosmic web model. Hydrodynamic simulations that include both dark matter and ordinary matter show how gas flows along dark matter filaments, feeding galaxy formation and creating the conditions for star formation. The Eagle and Illustris simulations demonstrate how cosmic flows carry both dark matter and ordinary matter along filamentary structures, creating the complex dynamics that shape galactic evolution. The local group S-motion through space reflects its position within the cosmic web and the gravitational influences of nearby dark matter structures. Our galaxy cluster is embedded within dark matter filaments that connect to larger structures like the Virgo cluster, creating gravitational channels that guide our motion toward regions of higher dark matter density. Warm dark matter models propose that dark matter particles have small but non-zero velocities that could smooth out the smallest scale structure while preserving large-scale filaments. These models predict subtle differences in how cosmic flows develop along dark matter currents, potentially explaining some discrepancies between observations and cold dark matter predictions. The discovery of dark matter streams within our own galaxy provides direct evidence for how dark matter flows create coherent structures. The Sagittarius stream and other stellar streams in the Milky Way's halo reveal the remnants of smaller galaxies that were disrupted by tidal forces, leaving behind trails of stars that trace the underlying dark matter currents. Fuzzy dark matter models suggest that dark matter might consist of ultralight axions that behave like quantum waves on cosmic scales. These models predict that dark matter currents should exhibit wave-like interference patterns that could create complex flow structures extending across vast distances. potentially explaining some observed features of cosmic flows that challenge conventional dark matter models. Direct detection experiments searching for dark matter particles have yet to definitively identify the nature of dark matter, leaving open the possibility that dark matter physics includes interactions or properties that could affect how cosmic currents develop. The failure to detect weakly interacting massive particles, WIMPs, has led to exploration of alternative dark matter candidates with different clustering properties. Gravitational wave astronomy provides new opportunities to study dark matter currents through their effects on compact object mergers. The LIGO and Virgo detectors have observed gravitational waves from black hole and neutron star mergers, and future space-based detectors like LISA could potentially detect gravitational wave signatures from dark matter structure formation processes. The cosmic microwave background radiation contains imprints of dark matter fluctuations from the early universe, providing constraints on how dark matter currents developed over cosmic time. The Planck satellite's precision measurements of CMB anisotropies reveal the initial conditions that led to current dark matter structure and cosmic flow patterns. Baryon acoustic oscillations, regular patterns in galaxy clustering, provide a standard ruler for measuring cosmic distances and flows. These oscillations, imprinted by sound waves in the early universe, allow astronomers to map how galaxies move relative to the underlying cosmic web structure and identify deviations from pure Hubble expansion that reveal dark matter current effects. The Euclid Space Mission and the Large Synoptic Survey Telescope, LSST, will provide unprecedented observations of cosmic structure and galaxy flows, potentially revealing dark matter currents with much greater precision than current surveys. These facilities will map billions of galaxies across vast volumes of space, creating detailed pictures of how matter flows along cosmic web structures. Modified gravity theories, such as modified Newtonian dynamics, MOND, propose alternatives to dark matter that could explain cosmic flows through modifications to gravitational physics rather than visible matter. However, these theories struggle to explain the full range of cosmic structure observations that dark matter models accommodate naturally. The relationship between dark matter currents and galaxy formation creates feedback effects where galaxy evolution influences local dark matter distribution. Supernova explosions and stellar feedback can redistribute ordinary matter relative to dark matter, potentially affecting how galaxies move along cosmic web filaments. Cosmic void regions, where dark matter density falls below cosmic averages, create complex flow patterns where galaxies move away from underdense regions toward filamentary structures. These void flows contribute to the overall cosmic velocity field and help explain why galactic motions show such strong directional preferences rather than random distributions. The discovery of cosmic flow coherence across scales approaching 1 billion light-years suggests that dark matter currents operate on much larger scales than initially predicted by structure formation models. This scale coherence challenges theoretical understanding of how gravitational influences can coordinate motion across such enormous distances through dark matter dynamics alone. As you contemplate that our galaxy moves along invisible dark matter currents that span hundreds of millions of light-years, recognize that you are embedded within the universe's hidden circulatory system. Every moment of your existence occurs within galactic motion, guided by gravitational flows from matter you cannot see, along cosmic highways that determine our destination through mechanisms that remain largely mysterious. The dark matter currents carrying our galaxy represent just one aspect of cosmic flows that extend toward even more enigmatic destinations. We must now investigate the evidence that our galactic motion points toward cosmic structures so massive and so distant that they challenge our understanding of how gravitational influences can operate across such vast scales. Chapter 4. Cosmic Flow Convergence. Our galaxy's motion toward invisible destinations is not an isolated phenomenon. It is part of a vast cosmic flow pattern where thousands of galaxies across hundreds of millions of light-years all stream toward common convergence. Zones suggesting gravitational influences that operate on scales larger than anything in our direct observation. These cosmic flows reveal that the universe contains organizational structures so massive they can coordinate galactic motion across distances that challenge our understanding of how gravity propagates through space and time. The discovery of coherent cosmic flows began with mapping peculiar velocities, galactic motions, beyond what cosmic expansion alone would predict across increasingly large volumes of space. The Seven Samurai survey revealed that our local group participates in flows extending across 50 million light-years. Subsequent surveys expanded this picture to show flows across 200 million light-years, then 500 million light-years, revealing that cosmic motion exhibits coherence on scales that initially seemed impossible. The Cosmic Flows Project, led by researchers including Helene Courtois, Brent Tully, and Yehuda Hoffman, has mapped galaxy motions across unprecedented volumes using increasingly sophisticated distance measurement techniques. Their work reveals that cosmic flows exhibit structure and coherence extending across scales approaching 1 billion light-years, distances so vast that light takes billions of years to traverse them. Yet gravitational influences somehow coordinate motion across these enormous regions. The cold spot in the cosmic microwave background radiation, discovered by the Wilkinson Microwave Anisotropy Probe, represents a region about 1.8 billion light-years across, where the ancient radiation appears slightly cooler than average. Some theories propose that this feature results from a supervoid, region of space with below-average matter density that affects cosmic flows and creates the observed temperature depression through gravitational effects. Bulk flow measurements reveal that our cosmic neighborhood participates in coordinated motion that extends far beyond local gravitational influences. The dark flow detected by Alexander Kashelinski and others suggests that galaxy clusters across distances exceeding 2.5 billion light-years exhibit coherent motion in a preferred direction, implying gravitational influences from structures beyond the observable universe or exotic physics operating on cosmic scales. The Shapley concentration represents one of the most massive known cosmic structures, containing over 8,000 galaxies organized into dozens of galaxy clusters spread across 400 million light-years. This enormous concentration of matter creates gravitational fields that influence galactic motion across vast distances, contributing to the cosmic flows that carry our galaxy and thousands of others toward this massive convergence zone. Computer simulations of cosmic structure formation struggle to reproduce the full amplitude and coherence of observed cosmic flows. The Millennium simulation and other large-scale structure models based on standard cosmology predict flows that are typically smaller and less coherent than observations reveal, suggesting that either dark matter distribution is more complex than models assume or that additional physics influences cosmic dynamics. The cosmic web structure, the largest scale organization of matter in the universe, provides the framework within which cosmic flows develop. This web consists of dark matter filaments connecting massive nodes where galaxy clusters form, separated by vast cosmic voids containing little matter. Galaxies flow along these filaments toward the intersection points, creating the large-scale motion patterns that carry our galaxy toward distant destinations. Redshift space distortions in galaxy surveys provide additional evidence for cosmic flows by revealing how peculiar velocities affect the apparent positions of galaxies. The 2DF Galaxy Redshift Survey and the Sloan Digital Sky Survey detect these distortions as systematic changes in galaxy clustering patterns that reflect underlying velocity fields driven by gravitational attraction toward massive structures. The zone of avoidance, where dust in our galaxy's disk obscures distant cosmic structures, complicates efforts to map cosmic flows by hiding potentially important gravitational sources. Radio astronomy surveys that can penetrate this dust reveal galaxy populations and massive structures that were previously unknown, gradually filling in the picture of matter distribution that drives cosmic flows in our galactic neighborhood. Peculiar velocity surveys using type Ia supernova as distance indicators provide precise measurements of cosmic flows across vast distances. The Union 2 compilation and subsequent supernova surveys detect systematic deviations from pure Hubble expansion that reveal gravitational acceleration toward massive structures, confirming the reality of large-scale flows through multiple independent observational approaches. The dipole repeller, identified through analysis of galaxy motions in our cosmic neighborhood, represents a large cosmic void that contributes to local flows by providing a region of below-average gravity from which galaxies are effectively repelled. This underdense region works in combination with massive attractors to create the complex flow patterns that determine galactic motion across hundreds of millions of light-years. Gravitational wave observations provide new opportunities to study cosmic flows through their effects on compact object merger rates and distributions. Future space-based gravitational wave detectors could potentially map large-scale structure through gravitational wave sources, providing independent constraints on the matter distribution that drives cosmic flows. The cosmic microwave background quadrupole moment, the second largest angular scale variation in the ancient radiation, provides constraints on bulk flows and cosmic anisotropy. The relatively low amplitude of this quadrupole moment limits how large bulk flows can be while remaining consistent with observations of the early universe anisotropy and homogeneity. Weak lensing surveys map dark matter distribution across cosmic scales by measuring how gravitational fields distort the shapes of background galaxies. The Dark Energy Survey, the Hypersuprime survey, and future projects like Euclid will provide unprecedented maps of dark matter structure, revealing the gravitational landscape that drives cosmic flows with increasing precision and detail. The Local Void, a region of below-average galaxy density extending across 150 million light-years and partially surrounding our local group, contributes to cosmic flows by creating gravitational gradients that accelerate galaxies away from underdense regions toward higher density structures. This local underdensity helps explain why our cosmic neighborhood moves toward distant massive concentrations. Constrained simulations that attempt to reproduce the observed cosmic structure in our local universe reveal that cosmic flows require specific configurations of matter distribution to match observations. These simulations suggest that our cosmic neighborhood represents a somewhat unusual region where flows are stronger than typical due to the particular arrangement of massive structures and cosmic voids. The cosmic flow velocity field can be reconstructed from galaxy surveys using techniques that assume gravitational instability theory and standard cosmological models. These reconstructions reveal potential flows extending to the boundaries of current surveys, suggesting that cosmic motion patterns might continue beyond our current observational reach toward even more distant and massive structures. Multi-tracer analyses that combine different types of galaxies and cosmic structure indicators provide more complete pictures of cosmic flows by reducing systematic uncertainties and cosmic variance effects. These approaches reveal that cosmic flows show consistency across different galaxy populations and survey methodologies, confirming their reality and ruling out most systematic error explanations. The relationship between cosmic flows and dark energy, the mysterious component driving cosmic acceleration, remains poorly understood. Some theoretical models suggest that dark energy properties could influence large-scale flows, while others propose that apparent cosmic acceleration might actually reflect local flow effects rather than global cosmic expansion properties. Future observations by facilities like the Large Synoptic Survey Telescope, the Square Kilometer Array, and the Extremely Large Telescope will provide unprecedented views of cosmic structure and flows across vast volumes of space. These observations will map billions of galaxies and reveal the three-dimensional architecture of cosmic flows with precision that could finally explain the gravitational sources driving our galaxy's motion toward invisible destinations. As you consider that our galaxy participates in cosmic flows involving thousands of other galaxies across hundreds of millions of light years, recognize that you are embedded within organizational patterns that operate on scales larger than anything in direct human experience. The cosmic flows carrying our galaxy toward distant destinations represent evidence for gravitational structures and influence mechanisms that exceed our current understanding of how matter and gravity organize themselves across the largest cosmic scales. But cosmic flows represent just one aspect of the mystery surrounding our galactic motion. We must now explore how the apparent weakness of gravity over cosmic distances creates puzzles that might require exotic physics or hidden matter to explain the forces pulling our galaxy toward invisible destinations. Chapter 5. Gravity's Cosmic Reach. The forces pulling our galaxy across hundreds of millions of light years toward invisible destinations raise profound questions about how gravity operates on cosmic scales and whether our understanding of gravitational physics remains complete when applied to the largest structures in the universe. The ability of distant matter concentrations to influence galactic motion across such vast distances challenges conventional wisdom about gravitational propagation and suggests either hidden matter distributions or modifications to gravitational physics that become apparent only on cosmic scales. Newton's inverse square law of gravitation predicts that gravitational forces should weaken dramatically with distance, falling off as 1 over the square of the separation between masses. Applied to cosmic scales, this relationship suggests that only the most massive nearby structures should significantly influence galactic motion, with distant structures contributing negligible gravitational effects despite their enormous masses. Yet observations reveal gravitational influences operating across distances where Newtonian gravity should be far too weak to coordinate large-scale motion. Einstein's general relativity modifies our understanding of gravity by describing it as curvature in spacetime, geometry rather than a force. But the basic inverse square relationship remains valid in most astronomical contexts. General relativistic corrections become important only in extremely strong gravitational fields or at very high velocities, conditions that don't apply to the gentle cosmic flows observed in our galactic neighborhood. This suggests that either exotic physics operates on cosmic scales or that conventional gravity acts through matter, distributions we have improperly identified. The problem of gravitational coherence across cosmic distances becomes apparent when calculating light travel times across the regions where flows are observed. Gravitational influences propagate at the speed of light, meaning that coordination of galactic motion across 500 million light years would require 500 million years for gravitational signals to cross such distances. Yet cosmic flows appear to show coherence across these vast scales, suggesting either that the gravitational sources are much more massive than visible matter indicates, or that the coordination developed over extremely long time periods. Modified gravity theories, such as modified Newtonian dynamics, MOND, and its relativistic extensions, propose that gravitational physics might operate differently on large scales than in the solar system, environments where it has been most precisely tested. MOND successfully explains galaxy rotation curves without requiring dark matter by modifying how gravity works at low accelerations, but extending these modifications to cosmic scales remains theoretically challenging and observationally uncertain. The FR family of modified gravity theories proposes that the Einstein-Hilbert action of general relativity should be modified by additional terms that become important on large scales. These theories can potentially explain cosmic acceleration without dark energy and might also affect large-scale structure formation and cosmic flows. However, these modifications must be carefully designed to avoid conflicting with solar system tests of general relativity. Extra-dimensional gravity theory suggests that gravity might leak into additional spatial dimensions on large scales, effectively weakening its apparent strength in three-dimensional space while allowing stronger gravitational effects through higher dimensional mechanisms. These theories could potentially explain both the cosmic acceleration attributed to dark energy and the large-scale flows that seem to require more gravitational influence than visible matter provides. Scalar tensor theories of gravity, including Brans-Dicke theory and its generalizations, introduce additional gravitational fields beyond the metric tensor of general relativity. These scalar fields can mediate long-range gravitational effects that might influence cosmic structure formation and galactic flows in ways that standard general relativity cannot achieve. Some versions of these theories predict gravitational effects that strengthen rather than weaken on large scales. The cosmological constant problem. Why vacuum energy appears to be 120 orders of magnitude smaller than quantum field theory predicts might be related to how gravity operates on cosmic scales. Solutions to this problem often involve modifications to gravitational physics that could also affect large-scale structure formation and cosmic flows, potentially explaining the apparent gravitational influences driving our galaxy's motion toward invisible destinations. Quantum gravity effects, while typically important only at microscopic scales, might accumulate to produce observable consequences on cosmic scales through mechanisms that remain poorly understood. Loop quantum gravity, causal set theory, and other quantum gravity approaches predict modifications to general relativity that could potentially affect cosmic structure formation and large-scale gravitational dynamics in subtle but observable ways. The holographic principle, emerging from black hole physics and string theory, suggests that gravitational physics in any volume of space can be described by information on the boundary of that volume. This principle implies that gravitational effects might propagate through mechanisms that differ from conventional field theory expectations, potentially allowing coordination of cosmic flows across vast distances through holographic information processing. Gravitational wave astronomy provides new opportunities to test gravity on cosmic scales through observations of how gravitational waves propagate across vast distances. The LIGO and Virgo detectors have confirmed that gravitational waves travel at the speed of light and exhibit the polarization patterns predicted by general relativity, but future space-based detectors could reveal deviations from general relativity on much larger scales. Dark energy, which drives cosmic acceleration and comprises about 68% of the universe's total energy density, might couple to matter in ways that affect large-scale gravitational dynamics beyond simple cosmic expansion. Quintessence models, phantom dark energy, and other dynamic dark energy theories predict interactions between dark energy and matter that could influence cosmic flows and large-scale structure formation. The coincidence problem, why dark energy density is comparable to matter density at the present epoch, suggests possible connections between dark energy and matter that might affect gravitational physics on cosmic scales. Some theoretical models propose that dark energy and dark matter interact through fifth forces or scalar field, couplings that can enhance gravitational effects on large scales. Emergent gravity theories propose that gravitational physics might arise from more fundamental quantum mechanical or thermodynamic principles that operate differently on different scales. These approaches suggest that Einstein's general relativity represents an effective theory that approximates more complex underlying physics, with corrections that become apparent on cosmic scales where conventional tests of general relativity are impractical. The cosmic web structure of dark matter filaments and nodes creates complex gravitational environments where conventional gravity calculations become computationally challenging. Unbody simulations of cosmic structure formation reveal that gravitational effects in these complex environments can create coordinated flows that extend much further than simple isolated mass calculations would predict, potentially explaining cosmic flow coherence through conventional physics applied to complex matter distributions. Screening mechanisms in modified gravity theories allow gravitational modifications to operate on cosmic scales while remaining hidden in local environments where general relativity has been precisely tested. Chameleon fields, symmetron mechanisms, and Weinstein screening provide theoretical frameworks for gravity modifications that become apparent only in specific cosmic environments, potentially explaining large-scale flows without violating solar system constraints. The equivalence principle, the foundation of general relativity, faces increasingly precise experimental tests that could reveal violations indicating new gravitational physics. Satellite experiments like microscope and future space-based tests will probe equivalence principle violations at levels that might detect modifications to gravity relevant for cosmic scale physics. Tidal effects from cosmic structures provide another avenue for testing gravitational physics on large scales through their effects on local gravitational environments. Precision measurements of tidal forces in our solar system could potentially detect the influence of cosmic flows and large-scale structure, revealing how cosmic-scale gravitational effects propagate to local environments. As you contemplate the forces pulling our galaxy across vast cosmic distances, recognize that these flows probe gravitational physics in regimes that remain largely untested by laboratory and solar system experiments. The coherent motion of thousands of galaxies across hundreds of millions of light-years represents one of the most dramatic manifestations of gravity in the universe, revealing either hidden matter distributions or gravitational physics that operates differently on cosmic scales than local environments. The mystery of gravity's cosmic reach demonstrates how much we still do and understand about gravitational physics when applied to the universe's largest structures. But gravitational puzzles represent just one aspect of our galaxy's mysterious journey. We must now explore the observational challenges that make it so difficult to identify what lies at the destination of our cosmic motion. Chapter 6. The Zone of Avoidance, the most gravitationally influential region in our cosmic neighborhood. The destination toward which our entire galaxy races at 2.2 million kilometers per hour lies hidden behind one of the most frustrating observational barriers in astronomy. The zone of avoidance where dust, gas, and foreground stars in our own Milky Way galaxy block optical observations of the distant cosmic structures that may be pulling us through space. This cosmic conspiracy means that the most important gravitational sources in our local universe remain largely invisible to the astronomical techniques that revealed their gravitational influence. The zone of avoidance encompasses roughly 20% of the sky, creating a band of obscuration that follows the plane of the Milky Way galaxy, where dust concentrations reach their maximum density. This cosmic dust, composed of tiny particles of carbon, silicates, and other materials produced by stellar evolution, absorbs and scatters optical light from distant galaxies, making them appear dimmer or completely invisible to optical telescopes. The cruel irony is that the most gravitationally active region in our cosmic environment lies directly behind this observational barrier. Interstellar extinction in the zone of avoidance can reduce the brightness of background objects by factors of thousands or even millions, effectively hiding entire galaxy clusters and superclusters that would be among the most prominent cosmic structures if observed in clear regions of sky. The dust absorption follows a wavelength-dependent pattern where blue light suffers more extinction than red light, and optical light suffers more extinction than infrared radiation, creating opportunities for specialized observational techniques. The discovery of the Great Attractor's location directly behind the zone of avoidance represents one of the most frustrating coincidences in observational astronomy. The gravitational mapping that revealed this massive structure's existence through its effects on galactic motions pointed toward a region of sky where optical observations face maximum difficulty, creating a situation where astronomers knew something extremely important was hidden but struggled to observe it directly. Radio astronomy provided the first major breakthrough in penetrating the zone of avoidance because radio waves pass through cosmic dust with minimal absorption. The 21-centimeter radio emission from neutral hydrogen in distant galaxies allows radio telescopes to detect galaxy populations that remain completely invisible to optical observations. The Parkes Radio Telescope, Arecibo Observatory, and other radio facilities conducted systematic surveys behind the Milky Way, revealing numerous galaxies and galaxy clusters in the Great Attractor region. The Dwingaloo Obscured Galaxy Survey used radio observations to discover hundreds of galaxies hidden behind Milky Way dust, including several massive elliptical galaxies and galaxy clusters that contribute to the gravitational field in the Great Attractor region. These discoveries demonstrated that significant galaxy populations exist in the zone of avoidance, but also revealed that the total number of detected galaxies still falls short of explaining the enormous gravitational influence inferred from cosmic flow observations. Near-infrared observations represent another powerful technique for penetrating cosmic dust because infrared light suffers much less extinction than optical wavelengths. The 2-micron all-sky survey, 2MASS, and the VISTA variables in the Via Lactea (VVV) survey used infrared telescopes to peer through dust clouds and reveal galaxy populations that remain hidden at optical wavelengths, gradually mapping the stellar content of structures in the zone of avoidance. The discovery of the Norma cluster, also designated Abell 3627, behind the zone of avoidance demonstrated that massive galaxy clusters can remain hidden until sophisticated observational techniques reveal their presence. This cluster contains hundreds of galaxies and represents one of the most massive known galaxy clusters in our cosmic neighborhood. Yet it remained largely unknown until radio and X-ray observations revealed its existence in the 1990s. X-ray observations provide another window through the zone of avoidance because X-rays from hot galaxy cluster gas can penetrate cosmic dust. The Rosette, Chandra, and X-Newton X-ray satellites detected hot gas signatures from galaxy clusters hidden behind Milky Way dust, revealing massive structures through their X-ray emission, even when their optical light remains completely obscured by intervening material. The Galactic Plane Survey, conducted by multiple radio telescopes, mapped neutral hydrogen distribution across the zone of avoidance, revealing large-scale structure and galaxy distributions that optical surveys cannot detect. These surveys discover bridge structures connecting visible galaxy clusters across regions of high dust extinction, demonstrating that cosmic web filaments extend through the zone of avoidance just as they do in clear regions of sky. Infrared space missions like the Spitzer Space Telescope and the Wide Field Infrared Survey Explorer (WISE) provided unprecedented views through cosmic dust by observing at wavelengths where extinction effects are minimized. These missions revealed galaxy populations, star formation regions, and large-scale structure features in the zone of avoidance that remained invisible to ground-based optical telescopes, gradually filling in the picture of matter distribution in gravitationally important regions. The systematic mapping of structures behind the zone of avoidance has revealed that this region contains numerous massive galaxy clusters and superclusters that contribute to local gravitational fields. The Centaurus cluster, the Pavo cluster, and other massive structures have been discovered through multi-wavelength observations, each adding to the total gravitational mass that could explain cosmic flow patterns while still leaving significant gravitational deficits unexplained. Gravitational lensing observations face particular challenges in the zone of avoidance because foreground dust and stellar contamination interfere with the precise shape measurements needed to detect weak lensing effects from background galaxies. However, advances in image processing and statistical techniques have enabled some gravitational lensing studies of dark matter distribution in regions of moderate dust extinction, revealing dark matter concentrations that exceed visible matter by typical cosmic ratios. The Square Kilometre Array, SKA, and its precursor facilities promise revolutionary improvements in radio astronomy as ability to map structures behind the zone of avoidance. These facilities will provide sensitivity and resolution that could detect even relatively low-mass galaxies through their radio emission, potentially revealing galaxy populations that contribute to gravitational fields while remaining invisible to all other observational techniques. Future infrared space missions, including the James Webb Space Telescope and planned extremely large ground-based telescopes with adaptive optics, will provide unprecedented capabilities for observing through cosmic dust. These facilities could reveal galaxy and cluster populations in the zone of avoidance with clarity approaching that available in clear regions of sky, finally providing complete catalogs of the visible matter that contributes to local gravitational fields. The dust extinction law, how interstellar absorption varies with wavelength, has been calibrated through observations of stars at known distances, allowing astronomers to correct for dust effects when they can be measured. However, the extreme extinction in the zone of avoidance often makes background objects too faint for reliable correction, creating systematic uncertainties in distance measurements and mass estimates for structures in these regions. Polarization observations provide additional information about dust properties and distribution that can help correct for extinction effects in the zone of avoidance. The alignment of dust grains with magnetic fields creates polarization patterns that reveal information about the three-dimensional structure of dust clouds, potentially enabling better corrections for extinction effects and more accurate observations of background cosmic structures. Machine learning and artificial intelligence techniques are being developed to identify galaxy candidates in heavily obscured regions through pattern recognition and multi-wavelength data. These computational approaches could potentially detect galaxy populations that human observers miss in regions of high stellar density and dust extinction, providing more complete catalogs of matter distribution behind the zone of avoidance. The frustrating irony of the zone of avoidance is that it demonstrates how local galactic properties can limit our understanding of cosmic scale phenomena. Our position within the dusty disk of a spiral galaxy creates observational barriers to understanding the very cosmic structures that most directly influence our galactic motion, making the study of local cosmic flows dependent on overcoming the observational limitations imposed by our galactic environment. As you contemplate that the destination of our galaxy's cosmic journey remains partially hidden behind dust and gas in our own galactic disk, recognize that this represents one of the most significant observational challenges in modern astronomy. The structures that most directly influence our cosmic fate remain largely invisible due to our position within the very galaxy whose motion we're trying to understand, creating a cosmic irony that highlights the observational challenges of studying the universe from within. The zone of avoidance continues to guard secrets about the gravitational sources pulling our galaxy through space, but advancing observational techniques are gradually revealing the hidden structures that lie behind this cosmic veil. Yet even as we peer through the dust, we discover that our cosmic motion points toward destinations that remain mysterious, for reasons beyond simple observational, OBSCURETION.